The range of weather extremes that we're experiencing today is already noticeably different, detectably, scientifically different than it was in the 20th century. And of course, the problem with that is that most of our cities, most of our infrastructure, the way we live our lives is largely predicated on the range of events that were experienced in the era when a lot of the world was, as it is today, was engineered and built and designed. But we're no longer living in that world. We're already living in a world where the likelihood of seeing extreme heat events or really heavy downpours is different than it used to be.
Typically the weather is boring, right? It is basically average, not affecting our life a lot. But the extremes is when we are far away from that, when suddenly it gets much warmer than average, or much colder than average, or much wetter, or much drier than average. So it is a state, or a day, or a week, or a month that is exceptional.
We humans are increasing not only the severity of these events so that they get more severe, so stronger storms, longer droughts, even larger extreme precipitation events, but also even the frequency is increasing.
Once you get to a warmer climate state, then the number of hot days and warmer, longer periods increase, and that has dramatically changed. So what used to be basically impossible 20 years ago has become almost mainstream these days, including events that go far beyond anything we've seen in the past.
An extreme event does not have to be historically unprecedented. And oftentimes we'll hear how could climate change possibly have influenced this event if an event of a similar magnitude already occurred before there was human-caused climate change? And the answer is that climate change usually isn't creating brand new types of extreme weather phenomena. What it's doing is essentially upping the ante on the kinds of things that already occurred. And making what was once perhaps an exceptionally rare event vastly more likely to actually take place today.
What is being quite dramatically shown in the real world today is that extreme events are playing out, I would argue, even in a more severe way than we had expected.
We've really seen a sequence of extraordinary extremes, ranging from the driest start to the rainy season on record in Southern California, which culminated with a powerful wind event and catastrophic series of wildfires, immediately followed by the heaviest snowfalls along the Gulf Coast of the United States that we've seen in the better part of 2 centuries, and a really extreme windstorm in Western Europe that followed shortly thereafter, something the likes of which haven't been seen in the past 100 to 200 years.
What we're currently seeing is often events in combination as we have not seen them before. So thinking about a very hot and dry period, then you have the forest that is destroyed by a huge fire as we had in California or Greece or Portugal. And then if you have a heavy precipitation event following that, if it falls on a forest that is already burnt out, are far more devastating. So seeing these events in combination, we call them compound events.
The pair of devastating wildfires that occurred in the Los Angeles area early in 2025 were a classic example of what's sometimes called a compound extreme, in that multiple constituent events created an outcome that was more severe than the sum of its parts. In this particular case, an unusually wet period in the 2 years leading up to the fires in LA led to highly abundant, unusually abundant growth of grass and brush, the main kind of vegetation that burned in these fires, leading to more potential fuels for the fires to come. Then we had an exceptionally dry and hot period during the fall, and then a record dry start to the rainy season. That really set the stage by drawing out all of that extra abundant fuel. And then, when we had a strong offshore wind event that drove these fire ignitions in early January, we really had this 1, 2, 3 punch, this record dry grass and brush because of the dry spell and the warm conditions that followed, and then this really strong wind event that helped push these conflagrations and turn them into a regional catastrophe.
I think we're starting to see indications of what I would define as super extremes, meaning that a super extreme becomes occurrences like what we saw in British Columbia, and probably what we're now seeing in Los Angeles, where it's not only an extreme, it's not only one drought or one precipitation event or one storm, it is something that interacts, and that these do not cancel out each other, but they actually amplify each other. That is too early to say as a trend, but we're starting to see signs of this occurring. And this is occurring at unexpected time of the year as well, as a winter occurrence. The same was the case in Germany when we had the devastating floods. They were unprecedented. European region getting half-year annual rainfall as one downpour, where a 20 millimeter rainfall event is a big rainfall. And here you have over 200 millimeters just smashing in. That was clearly a super extreme. And it occurred in July. It was in the middle of the summer, when normally you have the lowest levels of precipitation. So it's not only that it may be the first signs of a trend towards super extremes, they seem to, let's say, violate the very basic logic of seasons as we've had it. We're so dependent on the predictability of the monsoon winds, of the large regional weather systems. And if they are starting to show new behavior and moving latitude-wise and temporally, then of course things become more chaotic.
Pretty much over the whole planet, we see a very distinct trends over the last 70 years that heat extremes have become much more frequent. They now occurs already 5 times more frequent in a 1 degree warmer world, and now we're already closer to the 1.5 degree warmer world, where we expect this to be about 9 times as frequent. And this effect is actually going to continue with every additional tenth of a degree or every increment of warming as we continue to warm the planet.
Climate change is worsening the types of extremes that are already familiar. But there's also this tendency for climate change to allow types of events that really didn't occur in certain places to newly emerge there. So there are both kinds of risks, that what's already familiar will become even more pronounced, but also that in some places things that you genuinely haven't seen before will begin to occur. And indeed, we've now seen that in any number of record-shattering heat or precipitation or wildfire events occurring in places where they were not physically impossible, as evidenced by the fact, of course, that they did occur there, but were viewed previously to be unthinkable in those locations. And I think what we're seeing is that the unthinkable is becoming quite possible in many settings, just as the sort of more ordinary or more expected extremes in certain places are also becoming more intense and more common.
What we need to explore more in detail, and what we're seeing indications of, is that different processes that regulate extremes events on planet Earth are occurring simultaneously and interacting and reinforcing each other. So number one is we turn up the temperature on Earth. So the planet gets warmer, you get more evaporation and more moisture, and therefore more heat and more power that can trigger extreme events. I mean, that's the basic step one that can give stronger storms, stronger hurricanes, more floods, more severe droughts. That is well established. But then when that interacts with changes in the ocean circulation, then the slowdown of the AMOC and impacts on the El Niño-Enso dynamics, this can impact on the big regional monsoon systems, for example, which then adds to that general powering up. And when that in turn interacts, and the third part, with the changes we're seeing in the jet streams, in this case the polar jet stream.
Sometimes we see particularly wavy configuration of the jet stream, that river of high velocity air that defines the storm track. And when that happens, it tends to result in concurrent extremes in different places. So essentially, that one feature of the atmosphere, that wavy jet stream, essentially is a causal factor in producing extremely cold temperatures in one place and then extremely warm temperatures in an adjacent region. Likewise, extreme dryness and extreme wetness in different parts of the world simultaneously. This is a fundamentally important feature of global climate because it usually defines not only the path that storms take, but the degree to which cold polar Arctic air can escape the Arctic or the Antarctic respectively and make it to the mid-latitudes, and accordingly also controls how much very hot desert air from the tropics and subtropics can make it to high latitude regions. And so essentially, when we see very extreme heat waves or cold air outbreaks in a given place, usually that's the result of an unusually wavy pattern in this high altitude wind current known as the jet stream. And there's some evidence that what's going on is that there is what some scientists have called a tug of war between the Arctic and the tropics. In the Arctic, the air is warming much faster at lower altitudes than on the rest of the planet. So when we hear that the Arctic has warmed between 2 and 4 times as fast as the rest of the world, that means that the lower atmosphere in the Arctic is indeed warming much faster than the rest of the planet. But it's actually reversed if you look at the tropics, where the upper levels of the atmosphere are fastest warming there. And so this is where the tug of war idea comes from, which is that the Arctic is warming very rapidly at lower levels and the tropics are warming very rapidly at upper levels of the atmosphere. And because the jet stream is primarily caused by this temperature differential between the tropics and the Arctic, these changes might be hugely consequential for its behavior and position.
We're seeing indications that these changes in these large systems may be interacting. So temperature rise, ocean heat conveyor belt, polar jet stream. Combine that then with changes in drying out of landscapes. So the ecosystem impact finally on green water drying out, land degradation, loss of ecosystem functions, very unresilient management systems. Put that all together and you have quite a disturbing cocktail.
We know that many types of extreme weather events are becoming more frequent and more severe in a warming climate. This has been observed already in history to date, and it's an even stronger expectation that it will emerge in many cases more strongly and in additional regions with even a small amount of additional warming. So this is something that we expect to continue to unfold in the coming decades. The strongest evidence for increases in extreme events is those that relate directly to temperature, so things like extreme heat waves, for example, and also to moisture in the atmosphere. So the very heaviest precipitation events, the heaviest downpours becoming even more intense, and the worst droughts becoming even longer and even deeper. And there's evidence for other kinds of events connected to those as well, but these days the strongest evidence we see is for heat waves and for heavy downpours. And as the climate continues to warm, the range of extremes that are directly attributable to climate change will grow substantially.
The phenomenon where we see most of the most dramatic changes are heat waves. And there we do actually see and have been seeing events over the recent past which came even as a surprise to many of us who've been studying this for years or even decades. And one of the most prominent examples was the Pacific Northwest heat wave. Late June, early July 2021, 49.6 degrees centigrade in Canada. That was very well predicted by the weather forecasters, 10 days, 5 days ahead. And this is an event that is really hard to put into context of the gradually warming climate. Right? We would expect the extremes, the heat wave to become more and more intense, but suddenly having these big jumps, which we refer to record-shattering extremes, to make a difference between the record extremes, which typically are maybe 1/10 of a degree warmer than the previous record. This was 5 degrees warmer than anything previously observed. And so this put a lot of the things into question. And we studied this event. It turns out that it was, number one, a consequence of the very, very rapidly warming background climate, and then just a very unusual combination of well-known factors. So it's interesting, it was not even new processes that played in, it was actually the same ingredients, and you needed a lot of ingredients for a heat wave, and they need to perfectly play together to get such an intense event. This in combination of a very, very rapidly warming climate that suddenly produced these very big jumps.
So in a heat wave, typically you get a relatively stationary high pressure system. So a weather situation that doesn't change for a few days, maybe even 5 days, 10 days and so on. Characterized also by subsidence, so air basically coming down from the top and heating up once it comes down. Often also amplified by not a lot of moisture available for evaporation from the ground. These are sort of the mechanisms that occur. So as we see higher temperatures, then basically these heat waves get stronger. From a what we call thermodynamic point of view, they could also change because of different weather situations or weather situations staying in the same place for a very long time.
For a heat wave to happen, we need to have several ingredients. So one important one is to always need to have a high pressure system. We call it an anticyclone, that is turning clockwise. In an anticyclone, in a high pressure system, some people refer to it also as a heat dome, you have subsiding air masses. So the air masses are going from higher elevation to lower elevation. By doing this, they get compressed. That's very simple physics, like you can observe in a pump that you use to pump your bicycle or so, and you produce heat by compression. So if you put the air parcel in the top of the atmosphere and let them go down, they are compressed because there's always higher mass above them, and by doing so they warm up. That's a very efficient heat engine. So this is one of the important factors. So you need to have this high pressure system. Because you have the subsiding air masses, you also prevent thunderstorm to build. The atmosphere becomes what we call very stable. That means that the temperature gradient, the temperature decline from the surface to higher elevation becomes relatively small. So you have a very weak decline of temperatures with elevation. That prevents thunderstorm to build. So you have little precipitation, you have subsiding air masses. The third effect that you have because of this, you also have very little clouds. And little clouds mean you have a lot of sunlight coming in. So you have these factors playing together. Because the high pressure system is rotating clockwise, it also tends to actually advect air parcel from further south. So in the Canadian heat wave, the high pressure system that was sitting over Vancouver and around the Pacific Northwest was actually advecting very warm air from the Pacific, from climatologically warmer region towards this. Now there was even an additional effect, and that was actually maybe a bit counterintuitive. A lot of these air parcels that came from the Pacific were very moist, and they were actually lifted up in the atmosphere, and by doing so they released heat because the vapor in this air parcel was condensating and this heat was released. And this heat that was actually produced through a stream of very humid air, we call it a warm conveyor belt, is actually something similar like an atmospheric river. So the transport of the moisture produced a lot of heat that was released that actually then fueled the high pressure system. So it made the temperatures at 5 kilometers, 7 kilometers over Canada very, very warm. So it was actually warmer air to start with that started to descend and additionally made this stronger. So now thinking about climate change actually makes many of these effects more pronounced. It makes actually this warming effect through moisture and condensational heat release stronger. Then basically you have stronger warming of the air that is descending. You have high insolation, and then this insolation even hits drier soils. And once the soils get drier, there is less evapotranspiration, and evapotranspiration typically cools the surface. So if that goes away, you actually produce an additional heating of the surface. So you have several ingredients that all of them get affected by climate change, which makes those heat waves stronger and stronger.
The predictability of a weather system and therefore the limits of forecasting depend on the weather situation, and they also depend on the size of the thing. So typically a heat wave would be predicted 5, 6, even maybe sometimes 10 days in advance, right? Because it's a very large scale stationary system. For rainfall events, if it's large scale, like the flooding in Austria, these were predicted maybe 5 days in advance. So in general, it's actually remarkable how well the forecasts are doing. Weather forecast has improved massively over the last 10 or 20 years, both through better observations. We can run those forecasts now at higher resolution, more frequent. We can not just run one forecast, but we run 10, 20, 40 different forecasts of the same event, basically, and then you get the spectrum of outcomes. So almost all of those events were extremely well forecasted. And in certain places, those forecasts were taken seriously and the public was informed and people knew what to do and how to be prepared. And in other places, not so much.
So Valencia got huge amount of rains within a day. I mean, these are amounts of rainfall that are unseen north of the Alps. Extreme numbers, we're talking about 600 to 800 liters within a single day per meter square. That is only possible in a place that has relatively warm temperatures. So what happened in Valencia is we're at the coast, and we had a so-called cut-off low, a drop of very cold air that was detached from the jet stream. That's nothing else than a low-pressure system at high elevation, with relatively cold air that's brought southward. And it moved over the coast south of Valencia. Now we understand that low-pressure system, they rotate counterclockwise. And by doing so, he was actually pushing air from the Mediterranean towards the coast of Valencia. The Mediterranean was very warm because it's the end of the summer. This means that a lot of moisture can evaporate, and we had very warm air moving over that ocean. So if you looked at metrics like dew point temperatures, which are telling us how much moisture there is in the air, this was spectacularly high. And this air basically directly moved towards the coast near Valencia. So we had very warm air from a very warm ocean that was basically transported by what's called a cut-off low, an extratropical cyclone, a low-pressure system, and these ingredients then produced very intense rains. Then specifically in Valencia, which caused the larger rains than elsewhere in the coast, we had very strong extreme thunderstorms that were continuing and basically started to refuel and rebuild for hours and hours and produced very intense rain. And the soils underneath were actually dry because it was dry before. So these heavy rains fell on dry soils, which were sealed. They'd actually have less infiltration of water. So a lot of this rain went into surface runoff and then produced this big flood. In the end, it was actually the river that produced the big devastation.
There are basically three mechanisms by which you can generate precipitation. In almost all cases, it's water mass is moving up and therefore cooling, and then there's too much water for the atmosphere to hold, right? So because colder air can hold less moisture, and then it condensates and it falls down. And it could be either by fronts, so cold fronts and warm fronts, meaning air masses sort of flowing on top or below each other and causing lift. Or it could be topographic lift, so simply mountains being in the way, right? And then the air mass has to move. And that's typically what we see in what we call the föhn situations, right? So you have moisture coming from one side and then the air masses move up, and then you get the rain on one side of the mountains and you get the dry conditions on the other side. And the third mechanism is really the thunderstorms, right? So you have sunlight heating the ground and then the air starts to warm up, and because warmer air gets lifted, it moves up, and then you get condensation, rain, and then you get again more energy from the condensation, more rain, more lift, and that causes the growing towers, what we see as thunderstorms typically in summer. But in almost all cases, It's a way of lifting up the air into a colder regime, and then the cold air has to get rid of the water because it cannot hold that much water.
When you see these massive floods, we're talking of a completely new realm. It's a new hydrological situation on planet Earth. And of course, we do understand the physics behind this, because we know that for every 1 degree Celsius of warming, we add a 7% moisture holding capacity in the atmosphere. So we know that when we increase the temperature on Earth, we also power up the hydrological cycle. So we get more fresh water, we get more evaporations, we get more moisture, we get more clouds, we get more precipitation, but we don't know where it hits. We are not surprised. It's just that still the aggregation of this is causing larger than expected implications so far. Where this will take us is very difficult to say.
So one of the key reasons why wet and dry extremes, so droughts and floods, heavy precipitation events, increase so rapidly in a warming world is that the water vapor holding capacity of the atmosphere increases exponentially, so by around 7% per degree centigrade of warming. This allows essentially the ceiling on how intense precipitation can become to rise rapidly, but also the ceiling on how intense evaporation can become to rise just as quickly. And so this expanding atmospheric sponge effect, as we've come to call it, really explains about 80% of why we're seeing such rapid intensification of the hydrologic cycle of drought, flood, and wildfire risk in a warming climate.
As us touching 1.5 degrees Celsius, extreme events are increasing, and they're costing the world more and more in really big sums. I mean, Munich Re released for the 2024 assessment, concluding that this is the most expensive year for extreme events ever, and that we're talking of several hundreds of billions of US dollars in costs for the fires, the floods, the heat waves, all the impacts of extreme events. And we know with 100% certainty that it will get worse before it gets better, because we are heading towards overshoot. 2024 just touched 1.5, causing unprecedented extreme events, but by 2030, 2035, we are very likely going to breach 1.5 in an IPCC defined terms with the moving 10-year average. And then we will have 30, 40 years of overshoot, meaning reaching 1.6, 1.7, perhaps even 1.8, before potentially coming back to 1.5 if we're able to phase out fossil fuels and avoid losing the resilience in the biosphere, the carbon uptake capacity in the ocean and land. So we should be prepared for even more extreme events in the near future. So that's the starting point. That's the reality we're facing.
As the climate changes, the envelope of what is physically possible shifts. And in many cases, it's shifting upward to events that are more extreme than we were used to historically. And the challenge here is our human society, our civilization, our built environment is largely predicated on the particular envelope of weather that we experienced when all of that infrastructure was first designed and built. And so a lot of that infrastructure is, for most intents and purposes, fixed in place. We don't update our bridges, our buildings, our water pipes every year or so. But the climate is shifting essentially much faster than we're updating that infrastructure. And the challenge is compounded in the natural world too, because ecosystems, they can adapt and evolve over many, many generations. But the pace of change, the shift of that envelope of the plausible weather conditions that we're experiencing in a warming climate is greatly outpacing not only our ability to adapt in the built world as humans, but also the ability of the natural world to adapt through evolution. And so essentially, the real challenge with climate change is that the envelope of the extreme weather conditions that we can possibly see is expanding faster than our collective ability to manage that rate of change.
Many regions will have to deal with things that they have never seen before or not at that level. There's a lot of ways to learn about those events. You can look at weather models run in warmer climate, you can look at climate models, and we have some of those tools available. Simply look at other places that have similar challenges already today, and then you know. I think the greatest challenge is not in not knowing, the greatest challenge is not being interested or not realizing that there's a problem in the first place, or not being able to convince the population to invest in that.
If we do preparation, we need to start very early on. If we start 10 days, 5 days, when the weather forecast comes out, we can do some last fixes, but it's too late. So I think the way we need to think is we need to prepare years ahead in terms of adaptation, to think what is the worst event that is possible.
Technically, warning systems are easy, right? The question is, can you implement it? And then you see differences across countries. Some countries have almost no infrastructure. A good example is the R flooding in 2021 in Germany, where the weather forecast was basically accurate, and some of the private weather services have even outspokenly warned about what's coming. But again, the government was not informed. They had no way of informing people. And then about 200 people died, right? If you have the mechanisms in place, other places like the US or Norway, they have systems where every phone that's within the reach of a certain antenna gets a push message, whether you like it or not, you get this warning and you make like a huge noise. And people are warned. So it's really a question of decisions made in the public infrastructure. Do we want those warning systems or not?
We often do have forewarning of these events at least a few days in advance, and sometimes a week or more in advance of them actually occurring. And this is one key factor that allows us to mitigate the harms, to evacuate people and move them out of harm's way, or pre-position disaster response resources accordingly. So this is a hugely beneficial aspect of modern meteorology, is that it allows us to prepare for extreme events, prevent a great deal of loss of life and a great deal of property damage and economic harm that would otherwise befall modern society. In fact, countries that have robust national meteorological organizations providing tailored weather forecasts for their countries often see return on investment on the order of 10 to 1 in terms of the economic losses averted based versus the cost of providing those extreme weather predictions in advance. So by most metrics, this is a hugely successful application of modern physical science to benefit society.
Proper system to warn people against prepared for those types of events, of course, is not something you implement in a few days. But I would say the information itself is maybe the easiest and the cheapest. So if you just manage to get it out to people so that they're warned, then that's one thing, right? And telling them what to do is also relatively cheap. If we think a bit longer term, then we need to think about adaptation on the ground. And that means systems of drainage, like where does the water go, how deep and how thick are those pipes, and so on. Whole infrastructures for hospitals, cooling if it gets too hot, and so on. And that type of infrastructure is of course relatively expensive, and it needs a few years to get built. But in all of those cases, what we're seeing as the cost of those measures is far less than the avoided damage. So €1 or dollar invested in flood protection saves you something like €2 or €3 in damage. So in all of these things, people always say, well, it's expensive. Yes, but if it hits you, it's even more expensive. So it's much cheaper to be prepared than to wait for things to go wrong and then fix it.
There are extremes of such a magnitude, as we've seen in any number of tragic circumstances in recent years all around the world, that even very well prepared regions struggle to cope with. I think the recent wildfires that destroyed the better part of 20,000 structures and killed dozens of people in and near Los Angeles is a good example of this, because Southern California, and in particular Los Angeles, is one of the most wildfire-prone and wildfire-prepared regions on Earth. There is a wildfire-fighting force that rivals that of some small nations' armies that can descend essentially on this region when there is an active fire period. And yet, even in that context, these recent conditions were so extreme that we still saw catastrophic loss and, tragically, large loss of life as well. If the magnitude is sufficiently extreme that even those preparations aren't always going to be enough. The natural world increasingly is able to throw at us events beyond what we can reasonably adapt to or mitigate the risks of fully. We often make difficult decisions in resource-limited environments. You could build a completely redundant fire flow situation for the city of Los Angeles, but it would take time and cost a lot of money and require a lot of political buy-in and probably higher public taxation to accomplish. The reality is that many regions can experience events beyond their ability to respond to them already in today's climate, and that's going to be increasingly true moving forward. So there will be difficult decisions to make about how we allocate our resources to mitigate those risks. Which expenditures, which choices are worth it to help ease that transition on a path toward more extreme events.
Adaptation will be a huge component of dealing with climate change, in particular because the mitigation aspect tends to be difficult and slow. We'll have to prepare for things that have not happened in the past. And it's really in the extreme events is where the huge thresholds are crossed and where the huge damages occur. It's not the 1 degree warmer in a sort of average climate, but it's the 5 degrees warmer in an extreme heat wave or the 20% more rain in an extreme flooding. And we tend to see the same patterns everywhere, that people adapt to the things that they have seen before. We've seen examples, and one of them is the New York City subway systems, where reinsurance companies were talking to the city and say, well, I think you should do something and you should get insurance for your subway systems. And the city said, no, it's never happened. Right? And then Sandy came and it flooded the subway. And then 3 days later, this city said, well, maybe we should think about insurance, right? So the fact that something has never happened, it makes it really challenging for people to imagine how it could be and to be prepared for those kinds of things.
What we're currently seeing is actually records all over the planet. You see heat records every week or month somewhere, and we only see this for heat. For cold records, they still occur, but they're very rare these days. And they should not be, right? We should see about as many heat records as cold records. There's an additional element to this. If you beat the records after having measured 100 years, you should only beat it by a very small margin. I usually use an analogy from athletics. Long jumping. The world record was set in the 1990s. To beat that world record today is extremely hard. If someone would beat the world record, you would expect it to be beaten by 1, 2, 3 centimeters. And not by a meter suddenly. But if we now see in a climate system temperature records being beaten by 5 degrees, this is a very, very strong indication that something is going on. It behaves like an athlete on steroids. It behaves like an athlete that is suddenly jumping 1 meter further than anyone that has tried it before, and is a very strong indication that something fundamentally is changing in our climate system.
If you look at the last crises that have happened globally, not just weather, that's true for war, that's true for the pandemic, it's true for the environment, it's true for almost all of those what we call crises. All of them were basically forecasted a number of years before, right? You could look into the academic reporting, in the government reports, all of these were kind of known, right? The pandemic was extremely well understood, but the people were only responding properly in places like Asia where this has happened before. They were kind of prepared and they knew, and in Europe, in the US, there was a complete disaster. Not because there was no understanding, but because there was no willingness to invest in infrastructure to prepare for something that people didn't know. So I think we're somewhat lost in not because we don't understand, but because we cannot convince the population that things might occur that are completely different from what we've seen in the past.
With human-caused warming, this accumulation of heat-trapping gases in the atmosphere, in some cases we're unearthing some of these historical or even prehistorical extremes that modern civilization hasn't had to deal with over the past couple of centuries. And it is precisely that reality that we're forced to confront as warming brings about transformational changes in the kinds of extreme events that are physically possible, not only today, but looking forward a couple of decades, the kinds of extremes that will be possible with another 0.5 degree centigrade of global warming will be even larger than we're seeing right now. And that actually, if you think about what we're seeing today, is deeply concerning.